Welcome back, folks. Last time we played around with this neat idea of taking a 2D region and spinning it around an axis to create a 3D solid. The question that we then wanted to answer was, what's the volume of this solid that we've produced? Today, we'll begin with one more example of this, where we rotate a 2D region about the y-axis. Here, our region is enclosed between the curves y equals 2x and y equals x squared over 2. If we draw out these curves, which is how you should begin every volume example, you can see that the region R lies between these two intersection points, which we can solve for by setting 2x equal to x squared over 2. We get x squared equals 4x, hence x equals 0 or x equals 4. And to get the corresponding y values, you could plug 0 and 4 into either of these two functions. You'll find that y equals 0, or at the other point, y equals 8. This region then rotates into the screen about the y-axis to produce our solid. And when it pops back out of the screen, we would see this mirror image over here on the left-hand side. As we've seen, one way that we could figure out the volume of this solid is to imagine slicing it up along the axis of rotation to produce thin discs or washers. In this case, we would need to slice it along the y-axis from y equals 0 all the way up to y equals 8. We'd end up with this series of washers. Here's one washer drawn at some value y. Now, folks, the big difference between this example and those that we've seen previously is that here, since we're rotating about a vertical axis, the thickness of each of these washers is this tiny little change in y, dy, right? It's not dx like it was when we rotated around, say, the x-axis or another horizontal axis. Therefore, our integral is going to have a dy in it. We're going to have to set up the volume integral with respect to y. The volume of the solid will be the integral from y equals 0 to y equals 8 of a of y dy. Remember, a of y dy is the area of the washer times the thickness. That's like the volume of the washer. And we're integrating or adding up those volumes along the whole stretch of the y-axis from 0 to 8. For the area of the washer, we know that it's calculated as pi times the outer radius squared minus pi times the inner radius squared. The outer radius from our picture seems to be given by this horizontal distance. It's the x value for the quadratic. Solving for x, we would get x squared equals 2y, so x equals the square root of 2y. That's our outer radius, right? Similarly, the inner radius in terms of y is given by this horizontal distance, the distance from the y-axis to the line, y equals 2x, which we could write as x equals y over 2. Therefore, using our formula for the area of a washer, we find that the volume of our solid is given by this integral here. At this point, folks, hopefully we can agree that rotating about a vertical axis was a little bit more annoying for us than rotating about a horizontal one. After all, we had to do this extra step of expressing everything in terms of y. It sure would be nice if there were another way to calculate volumes of solids around vertical axes that didn't require us to go through this extra work. And the good news is, there is. This new method for thinking about volumes will be our topic for today. Just like with the disk or washer method, we're going to imagine a 2D region being rotated about an axis to create a 3D solid. You can imagine, for instance, the 2D region below rotating about the y-axis. It moves into the screen, pops back out, reflected on the other side of the y-axis, and continues on its way. When it's rotated the full 360 degrees, it will have produced a solid that looks something like this. Okay, my drawing skills are not the best. I'll show you a better visual in a moment, but try your best to imagine this shape in 3D, noting that it has an empty space here in the middle. Now, folks, instead of slicing this shape into discs or washers like before, this time I'm going to try to imagine separating it into a whole bunch of thin cylinders. This is sort of like how a roll of paper towel can be thought of as a bunch of thin cylinders, with each cylinder being one layer of paper towel around the roll. A typical cylinder would be formed by starting with some x value, somewhere between a and b, then drawing in a little strip at that x value and following the strip as it rotates about the y-axis. The strip would pop out of the screen over here on the left-hand side, and on its journey, it will trace out this cylinder here. Folks, if you'd like a better visual of what's going on, check out this little animation I have. We have our 2D region in purple, and it spins around the y-axis to produce the solid that I attempted to draw above. We can even show the solid being separated into cylinders, all centered about the y-axis. Here, I'll unrotate the solid, and you can actually see the cylinders being formed. Those yellow strips rotate around the y-axis to produce the shells. The idea is if the shells are nice and thin, we can add up their volumes to accurately calculate the volume of our solid. With this in mind, we'll note that because the shells we're working with here are very, very thin, the volume of each shell is approximately equal to its surface area, right, the area around the shell, multiplied by this tiny little width, this thickness of the shell, which you can see from the picture here is given by this change in x, which I'll denote by dx. Okay, so we want to integrate or add up the area of the shell times dx. Let's investigate this further on the next slide. This formula for volume, the integral of a of x dx, is basically the same formula that we used when working with discs and washers. The only difference is that now a of x is not the area of a washer. It's not pi times the outer radius squared minus pi times the inner radius squared. Now it represents the area of a typical cylindrical shell. If you've forgotten the formula for the area of a cylinder, I'll quickly remind you that it depends on the cylinder's radius, r, and its height, h. To get the specific formula, you can imagine snipping the cylinder from bottom to top and unrolling it into a flat rectangular sheet. The height of the rectangle is given by the height of the cylinder, h, while the length of the rectangle is given by the circumference of the cylinder, which is 2 pi r. Thus, the area of the rectangle, which, by the way, is the surface area of this shell, is 2 pi r h. Folks, we now have a formula that we can work with to calculate the volume of a solid by cylindrical shells. We need to integrate a of x dx, where a of x is 2 pi r h. R and h are the radius and height of a typical cylinder. Let's try out this formula to give you a good sense of how to use it in practice. Okay, in this example, we're looking for the volume of the solid that we obtain by revolving a region r about the y-axis. Here, r is the region between the graph of y equals 1 over x and the x-axis from x equals 1 to x equals 2. Folks, this is actually the region that we saw on the earlier slides. I've sketched it down here. We're now ready to see the calculation through. When this region rotates about the y-axis, it pops out of the screen reflected on the left-hand side here. I find that drawing this reflection in your picture helps to more easily see the cylindrical shells, so I suggest doing it. A typical shell starts as a strip at some x value between 1 and 2, say something like this. As it rotates around the y-axis, it generates a shell, which I've drawn here. We know that the volume of the solid will be the integral from x equals 1 to x equals 2 of a of x dx, where a of x is 2 pi r h, the area of this typical shell. The question we must answer now is, what is r and what is h? If you've drawn a good picture, you should be able to see these quantities pretty quickly. The radius of our typical cylindrical shell is this horizontal distance here. It's simply the value of x where we chose to draw the strip. And the height of the cylinder, h, is given by the height of the function 1 over x. Thus, the volume is the integral of 2 pi x 1 over x from x equals 1 to x equals 2. Oh, would you look at that? These two quantities cancel perfectly, and we end up with the integral of 2 pi dx. We get 2 pi x from x equals 1 to x equals 2, which evaluates to 2 pi times 2 minus 2 pi times 1. Folks, I'm getting a final answer here of 2 pi. I have one more example for you, folks. You have all the tools to tackle it yourself, so I encourage you to pause the video and try it on your own first. In this problem, we're considering the region between y equals sine x and the x-axis from x equals 0 to x equals pi. We imagine rotating this region about the y-axis, and the question asks us to set up the integral for the volume of the solid. If you're curious what the solid looks like here, check out this animation. It sort of looks to me like a half bagel with not much of a hole in the middle. Here, you can even see the solid separated into those thin cylindrical shells that we're going to use to calculate its volume. Pretty cool, eh? Just as before, we're going to sketch the mirror image of our region on the other side of the y-axis, and we'll draw one cylindrical shell generated at some point x between 0 and pi. We can see from the picture that the radius of the shell is x, and the height of the shell is sine x. Thus, the volume of the solid is given by the integral from 0 to pi of a of x dx, where a of x is 2 pi rh, in this case 2 pi x times sine x dx. The question isn't asking us to evaluate this integral, but you can do it if you want some practice. I think you'd need integration by parts here, and the answer you should get is 2 pi squared. I really like this example because it's one that would be really challenging to set up using discs and washers, but it's pretty easy to set up using shells. Indeed, think about what a typical washer might look like the one shown here. Its outer radius would be given by this half of the sine curve, while its inner radius would be given by this other half of the sine curve. You would need to find some way to separate the sine curve into two pieces in order to set up this integral. Plus, everything would need to be in terms of y, not x. Yuck. However, with cylindrical shells, the process was relatively painless.